Let's practice our bitwise operations. We're going to work on a problem that aims to reverse the bits of a number. Recall that numbers on computers are represented in a binary format with zeros and ones. These are represented as base 2 numbers, which is what binary means, and our goal is to take these zeros and ones and reverse their order. So, for example, if we had the number 1, 0, 1, its reverse is already what it is, so 1, 0, 1 backwards is 1, 0, 1. If we had the number 1, 0, 1, 0, then we reversed it, then we would have the number 0, 1, 0, 1. And that's our goal. We want to make a program that takes in a number and reverses the bits efficiently. And to do that, we need some bitwise operations. Let's get started. Let's start with an example. We have the base 10 number 11. 11 in base 2 is 1, 0, 1, 1. You can learn how to convert these numbers in a different video. Now, if we have the number 1, 0, 1, 1, and we take it backwards, we should just have 1, 1, 0, 1. And that's our number backwards. To do so efficiently using binary and bitwise operations, let's use bitwise operations by hand to do this reverse. Alright, so we have our input, which is to reverse 1, 0, 1, 1. And I've made a chart of inputs and outputs, so we can just see what's happening to our input as we generate our reversed output. So our input is 1, 0, 1, 1. But recall that integers are stored with 8-bit representations. So even though 1, 0, 1, 1 is 4 digits, which means it's 4 bits, we're going to pad the left with zeros. This is no different from saying that 12 is the same as 0, 0, 0, 1, 2, because they're equal. It does make sense to remove those zeros because usually we don't need them. But for the purposes of this problem, it's important to see the full representation of our integers so we can see what happens throughout the problem. So we'll write down our input and go from there. Alright, now we have our input padded with zeros. Our output can just start at 0, and remember that'll be padded all the way up to 8 digits, so we'll have 8 zeros. 0 is a good starting point for most bitwise problems and most number problems in general. If we need to change it later, we can do so, but for now I think it'll work. So let's write down our initial output and figure out what we can do to reverse these bits. Great, so now that our input and output are set up, let's figure out what we're going to do. A quick heuristic with bitwise algorithms is to start by checking the last digit of your input, and so we'll look at the last digit of our input to see if it's a 1 or not. To do that, we'll use the bitwise AND operator. The bitwise AND operator works kind of like a logic gate. So if you think of 0 as false and 1 as true, it'll just do false and true like truth tables with it. So for example, 0 and 1 is equal to 0 because it's like false and true, which is equal to false. And 1 and 1 is equal to 1 because it's like saying true and true, which is equal to true. So we'll check the last digit of our input. If it's a 1, like it is here, we'll just add that to our output and leave it alone for now. There's not much to do, and we'll just knock the last bit off of our input by doing a bitwise shift to the right by 1. So let me show you what that means. First, let's add 1 to our output. Okay, and now let's knock off the last bit in our input by doing a bitwise shift to the right by 1, which means knock off the last bit, add a 0 to the left side, and that'll give us a new bit to process in the next iteration. Great, and so on this next iteration, let's look at our input. We see that the last value is a 1, so we're going to add that to our output. But before we do that, let's move our output over to the left, so do a bitwise shift to the left by 1 to make sure that we're working with a new bit. We don't want to add 1 directly to our old bit because what if that's not exactly the correct way to do things? Hint, it's not. If we add 1 to our output right now, the value will be 1, 0, which looks like 10, and that's not our current values backwards, so let's not do that. Let's do a bitwise shift to the left by 1 on output before we add the number to it. Perfect. Now that we've done our bitwise shift to the left, let's add 1 to our output. And that looks good. Now we can just do a bitwise shift to the right on our input and continue. Okay, in this case, we do a bitwise AND on our input and find that the last digit is not 1, it's 0. So we don't need to add 0 to our output. However, we should show that we processed our value. So to do that, we'll still shift our output to the left before shifting our input to the right. So you can see we're mirroring the actions to make sure that we're actually reversing the bits. Perfect. Now let's just do a bitwise right shift on our input and continue. And now we're at the last digit in our input, which means that we should stop iterating when we get to 0, which will be the next one. And we do that so that we don't just keep adding zeros to the right side of our output, because that actually changes the value. So on this iteration, we find that we do have a 1, and so we're going to shift our output again first, then add our 1 to it. And then we'll just shift our input to the right. Now let's add 1. And finally, let's do a bitwise right shift on our input, giving us a 0, which tells us that we no longer have to continue with our loop. And we're done. Our output is exactly the value of our input reversed in bits. And we know that we've completed it because a quick eyeball will tell us that 1011 backwards is indeed 1101. So now we just need to translate this into code. Let's do it. Now we have our function header called reverse bits that takes in an integer value x. Now I want you to recall that we're not actually going to be converting the x to a binary number, but performing these bitwise operations inherently works with the binary representation. Of course, to the computer it doesn't really matter, but just know that x will be passed in as a decimal number and our output will be decimal, even though the bits have actually been reversed. We'll start by creating our output variable, which will be 0. So let's have an output equals 0 and start with our while loop. Okay, now our while loop will go as long as our input is not equal to 0. We can work directly with x because it's an integer value, which means it was passed by value anyway, so modifying it doesn't actually change our initial value. So we'll use x, you'll use our condition that until x is equal to 0, we'll continue with our loop. Great, so while x is not equal to 0, the first thing we want to do is actually shift our output to the left by 1. Now, even though it starts at 0 and that won't do anything, this will make our life easier later when we first shift our output to the left and then add our number to it. So let's shift our output to the left by 1. Good, so next step in our while loop is to check the last bit of our input. So to do that, we'll just AND our input x with 1 and see if it's equal to 1. Okay, so if x and 1 is equal to 1, remember that we just add 1 to our output. However, let's keep using bitwise operations instead of addition, even though the performance difference isn't really all that much. To add 1 by using bitwise operations, we can OR our output with 1. So OR is the single pipe, and the reason it works is ORing our output by 1 will just use a logical OR, so it'll say 0 or 1 is equal to 1, 1 or 1 equals 1, and because we just did a bitwise shift to the left, we know our last digit in output is 0. So 0 or 1 is definitely going to be 1. So let's add that in. Great, so I know that looks a little bit like a 1 or a bracket, but it's definitely a pipe. So we're just doing output or 1. And then when we come out of this if statement, we just want to move our input to the right by 1, a bitwise shift to the right, to make sure that we knock off that last bit that we just processed, and then we'll keep going until our input reaches 0. Great, and now we've done a bitwise shift to the right on our x. And finally, all we need to do is return our output at the end of this while loop. And we're done with our reverse bits algorithm. All we should do now is analyze the time and space complexity. Our time complexity is fairly straightforward, so the only times that we do actual work are in this while loop, and it's while our input is not equal to 0. Because our input decreases in size by 1 bit each time, that means that our while loop is going to run linearly with the size of our input in bits. So if we take n to be the number of bits in our input, then our time complexity is linear in that n, so it's big O of n space, or it's time complexity. And finally, our space complexity is also very straightforward. The only variable we create or use are output and our input, which is x. And those are both integers, which means they always use the same amount of space in memory. So we're using constant space, which is O of 1 space complexity. And that wraps it up. That's reverse bits in a nutshell.